So shall I get right into that? Because today we have a pair presentation. Me and Dorian are going to explain you about how we battled COVID using generative adversarial networks. Since you guys, or Garrett told me you guys like code, we took a very code-first approach. And we want to highlight one of the libraries that we used in that, which is Sacred for machine learning experimentation collecting. So, but let me first tell you a bit about who we are actually. So first, it's me and Dorian. Dorian will do his own introduction later, which you can maybe already see of seeing him in the video feed. Me, myself, my introduction is I studied computer science at the TUE. I was the first generation of people that were able to do the data science and engineering master. And during my bachelor's, I already got heavily involved with the education surrounding the TUE. And I got really interested in this data science concept, especially since the Department of Computer Science and Mathematics was really jumping on this. So as a student advisor, I helped setting up the first few masters and bachelors in data science in the University of Eindhoven, but also in Tilburg and in Den Bosch. The Tilburg master that Dorian was able to follow after that. So that's a nice flow of students there. I've worked in a software company for 2.5 years where I set up the data science department. And I was actually surprised with how large the difference was between my data science skills I learned in university and what I needed in real life, right? A lot of you will know that there is a lot of, data cleaning involved, domain expertise, just working with servers, SSH, etc. As a computer scientist from background, for me, that was quite okay. But during my work, I also noticed with students that didn't have a formal computer science background, but did specialize in data science, that they were missing a lot of like the hands-on practical skills of coding and using servers and using Git. So a bit from that frustration, I started playing with the CEO of Fruit Punch, Buster, about how can we close this gap, right? And he was already setting up Fruit Punch as an organization. So the problem that we're trying to solve as Fruit Punch is there's just a lack of good AI engineers. So this is known by everybody. They aren't learned how to apply data science in the real world. It's basically just learning Python notebooks and learning how you can write out backpropagation in pure Python, which is very important to know, but not a very usable skill though. And also this way AI is just not getting its maximal impact, right? If we are teaching people it the wrong way and we're not teaching it people at scale, then we're never going to close this gap and it's not going to have the impact that it can have. So that's actually the vision of Fruit Punch. We want to solve humanity's greatest challenges by educating the next generation of AI engineers at scale and also redefine how they solve these problems, because we focus only on AI for good, meaning that all AI that we build, we want to connect to one of the SDGs, so one of the Sustainable Development Goals. So with that, we're building the platform for AI talent development. So how we do this is actually mostly through challenge-based learning and peer-to-peer learning. So we're setting up a community, currently about 1,000 people from all inhabited continents. And our main way of education would be our AI for Good challenges. So when we want to do an AI for Good challenges, we look for organizations, NGOs, companies, universities that have a data challenge. So they basically need to have a data set and a problem that they really want to solve. So we transform this into an AI for Good challenge, and we crowdsource a team of engineers from our community to solve that challenge. We take this into a 2-month or 2-month to half a year format, where we try to first get the domain there. We do some master classes on the domain specific technologies, but also on the domain itself. We teach the people the basic skills to get, for example, the high performance computing ready and all the basics that come before you can solve such a challenge. And then the team just starts challenge-based learning, right? They communicate with the stakeholders, they communicate with each other, they learn from each other, and that is how we do the things we do. We all try to scale this through a platform. So we already have a platform right now, which you can find on fruitpunch.ai, but we're actually building our own challenge-based learning platform where we also do a gamified learning journey for everybody. So if you join our platform for the first time, you'll be able to file, hey, these are my basic Python skills, these are my basic data science and my basic AI skills. And from there, the system will advise you in, okay, I would follow these courses, join these challenges, do this MOOC, and this way you can build your own profile in a really gamified way. But the most important thing that we do, so what we do in that session is accreditate your skills. And this accreditation is purely peer-to-peer and not on an authorized, how do you call it? So what basically happens when a university gives you a diploma, that's like an authority argument, right? So the University of Eindhoven is renowned as being a good technical university. Me having a diploma there makes that you trust me because the university says that I'm good. But that doesn't really prove any of your single skills. So if you join in the challenges that we organize as Fruit Punch, you actually collaborate with a whole team, and this team will peer-to-peer review each other. And at some point, these peer-to-peer reviews will actually prove, okay, this guy has the most solid Python refactor skills, but this guy has the most solid generative adversarial skills. And this way you build your own profile, which is actually hard accredited without an authority argument in there. But well, that's what we do. One of the, as I mentioned, the most important thing that we organize are these AI for Good challenges. And for one of those, we got this really nice team, which you see on the left here. This is Dorian and his team, Dorian on the left. And what they did is they trained generative adversarial networks to help in COVID diagnosis. But I'm not the expert here, Dorian is, so that's why I asked him to join in on this presentation as well. So I'll stop sharing my screen and allow him to take over.
Thank you for the introduction. All right, so this is me, I'm Dorian, and this is our team. And this is Bram, he was our project leader. We have Jari, Meerte and Jans. And for the last half year, we have been working for Fruit Punch AI to put our AI skills for good in the AI for Health project, segmenting X-ray images of the lungs using a conditional adversarial network. So what are we talking about if we're talking about segmentation? Well, here's a good example. Where first you have an X-ray image, and radiologists often need to segment this image in order to find good diagnosis. So what they do, they have an image of a person's lungs. They have to draw out by hand the edges of the lung. It comes up with a mask, and you can lay it over, and it makes it easier to come up with a diagnosis. This is quite a time-consuming activity, especially now during the COVID-19 pandemic. This is not very efficient. There's a lot of things these radiologists could be doing in the meanwhile, as in consulting patients or other things that would have been more highly valuable. So we wanted to create a machine learning model that was able to do this segmentation. And apart from the diagnostics, it's also important that if you would like to train a model to classify COVID or classify other types of lung diseases, it is important that your model will be trained only on what's happening inside the lungs. So for example, on the first image, you can see here a little medical device. If someone's in the hospital and they want to take a picture or an X-ray image, then they often have these kind of devices on top of them, which could trigger a machine learning model into thinking that this patient has COVID, even though it didn't even recognize anything inside the lungs. So that's why it's important. It's very good to implement this in hospitals nowadays, because due to the COVID-19 pandemic, mandatory that all new admitted patients go through an X-ray screening first before they are allowed on their inside the where they need to go inside the hospital. This takes a lot of time from radiologists, and we would like to take over with AI so they can spend their valuable time in a lot of better ways. So take off a part of their workload and optimize this with AI. But to train an AI to classify, let's say, COVID, it is important that they have the right input data and data that has been segmented. It's more easy for a model to be able to recognize only what is happening inside the lungs. So that's why it's important. And the way we wanted to do this is with a GAN, or in our case, a CAN, a conditional adversarial network for image-to-image translation. And this is a short schematic image of how our model looks. So the difference between a GAN or a GAN and a CAN, so a generative versus conditional, is that the generative model takes in a random input vector, and our conditional model takes in a input image, so it's not a random vector. Then our CAN exists of two models. We have our generator model and our discriminator model, and they work together to get a highest possible performance. So I'm just going to walk it through. We put in an image into the generator. The generator comes up with a generated mask, which is fed into the discriminator model together with real masks. Then this discriminator model is trained on that data to classify whether a mask is real or fake. And this binary classification is then passed back into the models to gain performance. Furthermore, our generator is built up from a UNet, which is often used in segmentation of medical data. And this consists of a couple encoder layers and decoder layers. And our discriminator is a pretty basic CNN that classifies real and fake. So here it gets a bit more technical. So here is how our generator model looks. First, we take an input image. It is passed through 7 encoder layers until it reaches a bottleneck layer, which is also a convolutional layer, and then goes through 7 decoder layers until it reaches a convolutional transpose layer, which then, with a sigmoid activation, creates a mask. But now, what is special about this convolutional network and why this is called a UNet is because for each encoder layer, it takes out the information and also passes it through to the mirrored decoder layer and concatenates that with the information that has come through the bottleneck. So here you can see a bit how these encoder and decoder layers are build up. The encoder layer is actually pretty simple. It only exists of a convolutional layer, some batch normalization and activation liquirelu. And our decoder layer is existing of the convolutional transpose layers, some batch normalization dropout if we want that. So experimented with that a little bit. And then after that, a concatenate layer where it takes in the information that's coming through the bottleneck, but it also takes in the skip information, which is coming from the encoder directly. And the reason why it does this is it can take a lot more information until the last layers. Here you can see how their generator is defined, but in code. So what we just saw in the scheme. So first we pass our image through the encoder blocks. We start off with small filters going up bigger and bigger and bigger. So downsizing our model or our image until we reach our bottleneck. Then we pass this through to the decoder model, which then takes this information from the bottleneck, but also from our last encoder block, and then upsamples our image again until it gets to the activation point where we get a sigmoid activation where we get ones and zeros for each pixel. And then you can see how a input will result in a certain output. For updating this model, we use the mean squared error and binary cross entropy on a with weights of 100 to 1. And with the sigmoid activation, which I already told. We also now we come to the discriminator. This one is a little bit easier to understand. It has 6 convolutional layers. It comes up with a input image, so the X-ray image of the lungs, and with a fake or real mask, and then concatenates these two, passes it through convolutional layers and batch normalization layers and leaky ReLU activation until it reaches a point where it is defined if it's a real or a fake image. And this discriminator is then trained with the binary cross entropy function or loss function. So that is a bit how our generator and our discriminator work. But now it's ideal if these two are working together to create an even higher performance. So that's what this function is for. We define the GAN here again. We take the generator model, our discriminator model, and our images, and some parameters for tuning. And we first off make sure that our discriminator is not trainable during this training, because if we make our GAN and our discriminator at the same time trainable, they will. It is very hard for one or the other to gain, because if one rises in performance, the other one automatically goes down, because because it's a game against each other. So, here you can see we define an image, we take our generator model and create a generated mask. Then we let our discriminator model decide if this output from the generator together with the input image is real or fake. And on that information, we then define our model and make sure our model is trained once again with the MSE and binary cross entropy. I also added some code here in how we defined our losses. And how we generated our real and fake examples to get to these losses. I'm just going to start here. So for our real examples, we're using, just the data set we have, and we generate a real target and a real image and a real mask. And for our fake samples, we just get a target which has 0 and a generated mask. The discriminator is then trained on a batch of these images and resulting in a loss value. This also happens for the generated examples and also happens for the GAN model, so our generator loss. And to evaluate this, we use a dice score, and I will give you a little insight on how that works, because to train a GAN model, it is difficult to get to a optimal performance, because as I already explained, as soon as the generator starts to produce more real images, it gets harder for a discriminator to classify if it's real or fake. So the one's gain is the other loss. So you can't really come to what they call like the Nash equilibrium, where both are at a optimal performance. So that's why we're just looking at the output images, and we're checking how much these generated images are actually overlapping with the true masks that we have from our data set. And this works in this way. Every overlapping pixel times 2 divided by all the pixels will give you a score. So when our generated image is exactly the same as our true image, we would get a dice score of 100%. And every pixel that is off, this will result in a lower dice score. And with this dice score, we were able to get a good insight in when our model was actually producing the most real masks, and where it was for the human eye also very hard to see which was if the mask was generated or not. And I will come to a bit of more results a bit later. But here you can see a little bit more, it's more visualized for what I meant. So this generator loss is going up and down every other epoch. And for the discriminator losses, it's even higher. I did add some mean values, so you can see that the loss is actually decreasing. But just looking at these two graphs, it is pretty difficult to see what is actually happening. So that is why we also needed the dice score to see if we're actually training something that is resulting in a good model. And here you can see the result of our model. We would get around 94% on the validation loss, which was pretty good, and the test dice of 93.6. So yeah, we were pretty happy with this result. We also tested it on different validation splits and some different initialization, which all resulted in the same results. So here you can see what we came up with. Some examples of an input image, some generated mask, and a true mask. As you can see, some masks have little specks where it's not completely perfect, but overall you can see that it's doing a really well job. And but I have to say, I didn't want to leave out any bad examples. So I added one mask that was very difficult for our model to segmentate. And if you're looking at the image, you can imagine why it was hard for the model to come up with a good mask. Because even if you're looking at the true mask, it is kind of doubtful to say that this is all still part of the lung, and this is really needed for the diagnostics and the classification. So yeah, that was our project. And if there are any questions, I'm happy to answer them.
Yeah, so thank you very much, Dorian. So there are a couple of questions that came through. So one question was, where did you get your data from? Was this given to you? Did you collaborate with somebody? And how big a data set did you actually get? And I guess the hidden question is, did you have enough data to get to meaningful results, or could you have done with more?
Yeah, you can always do it more, right? But no, we were working with open source data. We are still working on providing a fruit punch open data set for this project and to provide it for everyone. But most of our data are coming from Kaggle data sets, and we combined a few. But we also, because we were actually dealing with very small data sets of around 800 images with masks, and around 200 of these masks were not segmented properly. So our team decided that it was important to enlarge in our data set and to to improve the masks that weren't to our liking. So eventually we had around 1,000 images with bypassing masks. But this was still quite a small data set, and that's also why we choose to work with a conditional adversarial network, because they are known to be quite well performing on smaller data sets. But yeah, it's all open source, and we're still looking into it, how we're gonna publish it. And that's also a bit to the people from Fruit Punch. But yeah, that's also what we're working with.
Right. Very good. Very good. So then the last question before we pass it on to Sako to talk about Sacred, Nicola is asking, did you think on how to identify those tricky examples like what you're showing now? This is a tricky one. It's very clear that it's tricky because we're staring at it. And I guess the question is, do you have an idea or future work on how to identify these tricky examples?
Well, as you can see here, our mask is not really looking like the true mask. So the way that we found these kind of masks is because they just have the lowest dice score, as I was talking about. So yeah, all the images with a very low dice score, we can identify them and then decide if we want to keep them in our data set or maybe lose them. Or yeah, it's a bit for the person to decide who wants to train the following COVID classification or what other classification models.
Right. Very good. Very good. So thank you very much, Dorian. So I know that Sako's got a cool story to tell. I know we're a little bit over time, so I'm going to ask Sako to share his screen, and then we'll leave some time for some questions at the end if more people have some. So Sako, would you like to share your screen?
So to just also add on one of the questions that Dorian was just answering, we did actually collaborate with a medical organization called Mastro, who actually provided the problem and also provided the stakeholder, right? So they eventually weren't able to share their data with it, which is often a problem with medical institutions. They're very keen on their own data, so that was actually a shame. But they did also guide the project with their domain knowledge, which is actually a really important thing, right? There are a few biomedical engineers in the team here, but of course, people that really know why they would want such a solution, that's key. So they still helped us out a lot there. But that's not where I'm going to speak on further. I'm going to touch back on this GAN project as well, but we're now going to look into Sacred, which has this nice slogan that says every experiment is sacred. So what does Sacred do? Well, it keeps track of the parameters of any experiment you run. It helps you run experiments with different configurations. It saves the configurations of all the runs in a database, and it's able to reproduce your results. And you might think like, okay, I have many tools that can do this, or I maybe written my own ones. I actually tested multiple of these. MLflow is one of the most popular ones, at least as an open source library. And then, of course, you have many data platforms that also have some of these services like Data Eco, H2O, etc. But I never found any of these that were as flexible as Sacred. But I can tell you a lot about this, but I can also just show you, right? And again, Gareth told me you guys like code, so we're just going to go into that. So this is a little presentation notebook that I prepared, which is also available on my GitHub. And this basically goes into, okay, I'm going to take the most simple data experiment and then build it into a better and better Sacred experiment, right? So what I do here, first just install Sacred. Normally you also need to, we're going to connect it to a MongoDB, so you would need PyMongo, but in this case it's already in the standard Colab container. And DNS Python is only necessary since I use a MongoDB from Mongo Atlas, so the cloud platform of Mongo themselves, which actually offer free MongoDBs of up to 512 MB. So if you want to quickly test this, just create a Mongo Atlas account and get a small MongoDB there for free. The test data that I'm going to use is actually also, again, something that is by default in Colab. So Colab always comes with this sample data folder. I actually have no idea what this data is about, but I basically just need a NumPy array to do some experiments with. So I save the California housing test data of train data set as example data.numpy. And then I create my first experiment. So what I do here, import, of course, NumPy to load the data again. I chose to do a PCA algorithm on it, so I don't need to test this, and I have the mean squared error as an accuracy measure. So first I define my model, I fit my model on the data, I decode, in this case, as you might know, PCA principle.
Sorry to interrupt you, Sako. Can you zoom in a little bit just so that we can read the things a little bit better? Thank you. So I think that reads a little bit easier.
Yeah.
Some of us have got high resolution screens here. Thanks.
Yeah, no, that's fine. If I need to go further, just notify me. So as you might know, I chose for an unsupervised model here, principal component analysis, which tries to find the principal components. You can look at it as like a clustering algorithm. And you first, of course, train the data, you encode it, and then you try to decode it. And what you check is what's the difference between the encoding and the decoding, right? So here we do a super simple mean squared error. Apparently, I did that very, very badly. But that's not the point here. So I have this super simple machine learning experiment, and I have some score there. But now I need to okay, I'm going to try different versions of PCA, or I'm going to tune the hyperparameters and all this kind of stuff is going to influence this score. And I want to collect what changes lead to what changes in result, right? So this is where Sacred comes in. And to get to the most basic Sacred experiment, you just import Sacred, you create an experiment, give it some name. In this case, it's an interactive mode. The only reason to do this is because it runs in a notebook. Normally, if you would just run this in PyCharm or your other favorite Python IDE, you wouldn't need to do this. Well, you make sure that everything is in a function, which is something that you can basically better do anyway. And then you put this xmain over it. And that's actually just, it makes this function the primary function for Sacred to execute, which you can then easily do by doing xrun. So what it will do then, this is super basic, of course. It will, and you basically, what I forgot to tell, you return your results at the end of the main function, right? So that's also a difference in here. I printed that. Also, what the former speaker told, right? Not working with trying to work with function with actually objects instead of printing everything. Well, here we're doing the same thing, right? So we execute that, and what we get then is, well, some basic output. Something that's already very useful is that it computes how much time it took. Well, in this case, a Sacred experiment like this takes about no time, so that's nice. You can just run that really quickly in the notebook here. Well, of course, it crashes then. Oh, yeah, sure. Okay. But this is, of course, still not that useful. We actually want to be able to track the changes, not only see how long it took. Well, that is where the Sacred observers come in. And the first observer that we're going to include here is a file storage observer. So the file storage observer will basically just create a custom path in one of your drives, so in a file path, and there it will collect some files from the different experiments that you're running. So in this case, I just import the file storage observer from Sacred, and I append this to the observers of my experiment. So the file storage observer in this case only takes a base path, so a base there where all the files will be written to. So when I now run exactly the same experiment, I also get some output files in this run path. So what we see here is the cout, the config.json, the metrics.json, and the run.json. So if you just look into a few of those, the run.json actually just tries to make your experiment as reproducible as possible, not only in your own environment, but also in environments of your co-developers, right? So it takes all the dependencies that you have used with their versions, of course, the name of the experiment. It even has a heartbeat, the CPU. In this case, I'm not using a GPU, but also the GPU it would be hosting, the exact versions of Linux, exact version of Python, metadata, all this data that you might at some point actually thought like, oh, wouldn't I have liked to know if this had run on a GPU or not, on what type of GPU and what type of operating system, because I'm not able to debug it like this. So this is everything that it just saves by default. And of course, the start time, the stop time, and the status. In this case, the experiment is not running anymore. It has already completed, and it has also not failed. If we go into the config.json, this is quite empty. It only has the seed that it takes used by default. And if we go to the cout, this is actually not created since we're in interactive mode. So it's not possible to have a cout.txt when you use interactive mode, so in a notebook. But normally this would just contain the output of your terminal, right? So just every line as it would have ran in your terminal will be in the cout file. So how are we going to make this even more useful to us? Well, let's try and add some other data. We're going to define a config function. So we do this by doing the x.config operator above it and then defining some basic parameters which are important for our experiment. So the path of the data and which model we're using. Then we have just separated the part where we load in the data into a separate function, and we capture that as part of the experiment, as part of the sacred experiment. So, of course, you don't need to do this, right? You could basically also run this function without making it part of the sacred scope. But the nice thing about sacred is that every parameter that you define in the config will actually become a kind of global variable. Which you can then inject in any of these functions. So I don't need to pass the data path into the data function down here, and therefore also I don't need to pass it to the train data. I can just do this xCapture, make the data function part of the sacred scope, and then do import this config parameter in the definition of the function. So here again, exactly the same experiment, and we would get the same output files here. Nothing that new here, except that we now have defined a config, and therefore there will also be information in the config.json. So beside the seed, we now have, of course, the data path, but also the object that I defined, so the PCA with all the parameters in there, which again, if I'm going to do hyperparameter optimization, is very useful to have all the hyperparameters, so not only the ones that I set specifically, but actually all the parameters that the PCA object catches in here in the config file. So at some point you don't only want to record the basic result, right? As we saw before, I print this basic result and it's also saved into the config file, but we want to save, for example, the model itself. Well, there are a few ways of doing this. One of those is adding it as an artifact. So what I did here is I added one function, which is just a simple function to pickle an object. This is not part of the sacred scope, since it will not use any of the config parameters. But what it will do is at some point it will ask itself, okay, do I want to save this model? And then I add this artifact. I add the trained PCA model as an artifact. So what we would get then after running again, same experiment, we would be able, and besides that, I also appended the scores of a CSV here and also added that one to the artifacts. What we would get then is not only the cout config and the metrics and the run.json, but also this pickled file would be added to the same folder and to the same scores. So now all we've seen is using the file observer, which is really nice, of course, but it's also super limiting. So if I'm writing all this to my local hard drive, I can't share it with my fellow developers, but also it's really hard to query, right? What if I want to do cross-validation? So I want to run 20 experiments and I want to see if my accuracies are stable, or I want to compare a few experiments. I would need to write additional code to extract this from these JSON files and these TXT files. So of course, that's not the way to go. The way to go is actually adding the Mongo server. So as I mentioned before, it's really easy to create a small MongoDB using the Atlas platform of MongoDB itself. And here we then have one including the Mongo server. I actually always make sure to catch that behind that debug folder. You often just write an experiment, make some changes, run the experiment, and apparently you made some error in writing the calculation of the metric. So your whole experiment crashes while it has run for 2 hours. Well, that's a shame anyway, so I should have written better testing code. But anyhow, also when this happens, you don't want it to clutter your MongoDB. So in that case, I always just set a flag to debug it and then not write into the MongoDB. Here you see my Mongo credentials. I'm sure some of you have noticed. This account will delete itself tomorrow, so I'm not really worrying about it. But it is actually functional code, right? So it will right now connect to the database. Oh, it is definitely not doing that. I haven't run all this code. I guess I should do that. But anyhow, also here we see the same functions that we saw before, right? The config, the data, the main, nothing there is changing. What is changing? Oh, I missed the pickle function. Yeah, it's there now. No, it's not there now. Where did I find that? Here. Ah. Live demos, always dangerous. And I'm not as swift as a coder as the guy before me, so. But here we define exactly the same functions, only we now have this extra observer here, right? So all of the code is the same as in the previous cell, but we just decided to add an extra observer, the Mongo observer, which just has the authentication URL and the name of the database where I want this code to, where I want these artifacts to be written to. So now, besides having this data structure in my local drive, I also have it in a MongoDB somewhere in the cloud. And I'm just going to show you in a sec how you can extract that, of course. But as you all know, you can query MongoDB really easily. It's basically working with Python dictionaries, so it should be really usable for anyone who is very familiar with using Python. And this way you can just query all these different experiments and see, hey, how have I been doing over time? Create nice reports based on the live experiments that you are running right now. All these things are possible when you simply add this basically one line of code to your sacred experiment. Just to give you an example of a bit more complex experiment, here you have a simple Keras autoencoder. And there you would have some of the same code, like do I want to save the model and save the tensor board? The reason that I don't do this on debugging, of course, is that neural network would become way larger and would start to clutter my database and would start to clutter my hard drive. The same holds for tensor board files, which can become really large. So I only want to create those when I actually am running an actual experiment. This also changes, in this case, the observer path, so where it is writing the experiment numbers. And from there, we have a configuration which now holds things like batch size, encoding dimensions, number of epochs that I want to run the experiment. I have a data set where, in this case, I just create two data generators, a training and a validation generator, which I can return here. And that takes these global variables, the sacred global variables, for the data path and the batch size. Then I define a model function here. It takes the encoding dim and the batch size and just creates a really simple encoder-decoder model. And then I have an auto main in this case, which would mean that I don't have to X run at the end of the code. It just makes sure that it runs this code the moment that you run the experiment file. Here, just what you would expect when running any Keras model, compiling it, adding callbacks like the tensor board, fitting the generator, and then optionally saving the model, getting all the results from the history of Keras, and then returning those results at the end of the main function, right? So this one doesn't run, but the one that would run is this one, and it's the connect with GPU. So as you guys probably know, if you use Colab, you can actually use them with free GPUs in there. So if you, in the runtime, you change runtime type, you can set it to GPU here. So in this case, run anyway, I first have to Sorry, what is wrong? Oh, I've used too much GPU today. That's very, very sad. Well, I don't per se have to run the code, so that's not that bad. No live experiments anymore. That's sad for you guys, so I can't screw up. But here we mount a drive where we actually host the data set. So we will ask for some authentication here. Again, we install Sacred and DNS, Python, all the other packages that we need are already in the Colab environment. Normally we would get a Tesla T4 GPU, but in this case it has denied us any access on that. So from here we do the importing of all the packages, and this is actually the code that Dorian showed you just now, but then in the form of a Sacred experiment, right? So indeed, again, we have this defining an experiment. We have the config, in this case, a way more complicated one than you would have if you just define a simple PCA algorithm. So we have all the losses, all the parameters here that Dorian already explained to you. Here we configure the observer. So again, we have this Mongo observer and we have the file path observer. This again is, by the way, also just written directly back to a Google Drive on the Colab connection. We load the real samples, we get the names. These are all Sacred functions, and we don't have, and again, we keep clean code since we don't have to pass all these parameters here. We just give them to the function via the configuration of Sacred. These you might recognize, the bits of code that Dorian showed before, so the definition of the generators, etc., the compilation of the GAN, all these are part of the Sacred environment. And in the end, we would get to the main function. And here we start training the model. So we actually set the seeds. So if you remember, there was a seed in the config file. If you want to use this seed, you can just do _seed in any function. In this case, we want to set that to the same as the basic Python seed and the TensorFlow seed to make sure that our model is actually reproducible, right? So that's also a main reason to use Sacred. We load the data set, do all the things that you expect that you do when you try to train a neural network, calculate the losses. This is the code that Dorian also showed you. We're doing some early stopping here based on the dice metric. And at the end, we collect the results. So we see, okay, which epoch yielded the best loss and what was this loss. But of course, we also just want to have all the losses over time, right? So the standard deviations of those with the train and the validation loss as well. And where did we save our model as useful information? So this is all run through a Sacred experiment. This is what you would see during the running of it. So in this case, this was experiment 20 already for this specific version. And here it was able to get the best file loss from epoch 5. So if we then go over here is the simple graph that Dorian showed as well. What you want to do then, of course, is now all this information is in a MongoDB. So all the information, all the files that I showed you before are here again. I get this disconnected. I specifically reconnected them all just before the meeting started, but apparently that's too long ago. So the nice thing here is in a completely different environment. So this is a new Colab file, which is not connected to the other one at all in any way. Here I also do not make this connection to my Google Drive. So it's a completely standalone environment, but I of course connect to the same MongoDB. Here's just some super basic code helping me to extract the results from that. Which all of you would know if you have the basic Python skills. And this is actually what is inside a run. So here I didn't have any artifacts, but again, we have the config, right? So all the batch sizes, all the config parameters that you saw before will be in here and are all queryable in this dictionary. You can see the main path, the number of epochs, again, the versions of all the libraries. Here you see that this time I was able to use, when I ran this experiment, I was able to use a GPU. I got a Tesla K80 from Colab. I even got the host name of the Colab system and the Python versions, etc., that it ran. And then, of course, the results, right? Which result was the best? In this case, that was epoch 0. I only ran it for 1 epoch, so that's not too weird. And these are the losses that are collected here. This is just some simple code that is going over all the experiments that I've run so far, at least the first until the 25th experiment. And it will try to see which one did finish. So as you can see, I screwed up 17 experiments by writing bad code. So all of those crashed. But the next 4 experiments up until number 21 did actually succeed. And then you can just start querying those. So if I want to get the first of those, this would be experiment 19. Here you get, again, this dictionary back, and you can just start querying that and also collecting, concatenating the data, right? So that's the goal of doing it in a MongoDB, concatenating all this data, making reports, and this becomes really a lot easier for you and your team to collaborate on building experiments, making sure they're reproducible, and actually comparing their results. So that's actually about it. That's what I wanted to tell you guys about Sacred.
So Sako, this is very interesting. I really maybe you can answer a few questions that came through the system while we're here. So question number 1 was, this seems like a bit of overhead for a data scientist, right? So, you know, it feels like you're diverging from the essence of the math there. The question really is, how hard is it for someone who's a pure data scientist to pick up this and use it, right? So you articulated that there's value if you use it, but it has to be used, right? And the question is, how hard is this to be picked up by others?
Well, I don't know whom here has been like a junior data scientist and then at some point was doing exactly what you just now, me writing experiments, changing hyperparameters, and at some point thinking like, damn, I'm sure that I got a higher accuracy some time ago, but I have no idea how I configured that. And then looking back at your emails, trying to find if you maybe emailed the code to someone, you didn't use Git properly, damn. Oh, wait, you know what? I'm going to write some custom Python code to do this, right? I'm going to write some code that writes accuracy to a TXT file. That's going to help me. Okay, I'm doing that. 2 weeks later, you have exactly the same problem, but you don't remember if you ran it on the Linux kernel or on Windows, and you have some bugs that might have caused that. Oh, how did I do that? Again, starting to write this own custom Python code to try and record all this data. Well, as I showed you before, making an experiment into a sacred experiment just needs 4 lines of code. It's really easy for anybody to use. So, of course, if you want to go into the MongoDB and you want to query that, etc., you maybe need a bit more of the computer science skills than you would as a pure data scientist. But just adding the sacred code and being able to at least look back into the file observer and see like, okay, this is how I ran that experiment back then. This will also save you so much time in reiterating these experiments. And in that sense, also saving computational power, saving the environment by using less power. There's only advantages here.
So that's very good. So thank you very much for that. And it's nice that you showed it to the example that Dorian showed. You connected the dots. So thank you for that. Then the last question before we call it a day is, you showed a lot of code, and unfortunately some of us couldn't follow the code at the pace that you were talking. The question is, how can we see this? Will you share some of the links? Is this something that we could dive in at a later stage? Would this be something that you could share afterwards?
Definitely.
And if so, what would your recommendation be? On the YouTube comments of PyData Talk, would that be the right place to do it?
Oh yeah, I could paste it in there. Where you can already find it is at least the first notebook that I showed you. So the one where I changed this PCA experiment into a more and more complex sacred experiment. That's actually on my GitHub, which is Sako Arts concatenated. And also by going to sakoarts.nl/sacred, you actually will end up on this GitHub page. So you can just really see how you can step-by-step make this. I'll just type it into the.
So that the chat that you're typing, only the presenters can see. So we will share that later. But maybe just one last question is, and this actually is a good one, I should have thought of myself, is you're showing the parameters, but does Sacred also store the code that was used? So I think you only showed it stores parameters and incremental things, but does it also store the code, or is that?
Yeah. Again, this was
how is that coupled to each other? How does that work?
If you go to the notebook that I also that I'm going to share, that's actually in the text there. This is again a limitation of the interactive mode. But indeed, if you run it as a normal Python file and then don't use the interactive mode, then it will save all the code of all the experimentation code into a source file in the same folder where it leaves all the other stuff. And of course, then also in the database.
That's very nice. So I guess that comes to the point of why you said this is more flexible than some of the other solutions that you saw. This is maybe a good example where it speaks to it. So with that being said, I want to thank you ever so much.